Hi everyone, my name is Penny. I'm working for almost 2 years after graduation. And this is my first time standing on the Open Infrastructure Summit to address the session. I'm quite nervous and a little bit nauseous. So I prepared these notes. If you don't remind, I think I'm probably will be totally blank sometimes. So my topic is about Kata Containers ARM. I'll talk about our progress. This is my agenda. I will briefly introduce Kata Containers design, but I see some materials there. I will quick pass this slides. And I will talk about hardware requirements for running Kata containers on ARC64. And I will majorly talk about the two major work last year, NVIDIA DEX on ARC64 and memory held end on ARC64. So the Kata containers design. What is Kata Containers? I'm quoting from their official website. Kata Containers is an open source container runtime building lightweight virtual machines that seamlessly plug into the containers ecosystem. It can work with Docker, Kubernetes, OpenStack. You can see from my pick, it has 3 components, major components. Kata runtime, Kata agent, and Kata shim. And as for Kata users, you probably only care about one component, Kata runtime. Kata runtime is just like runc, it's OCI compatible, so anywhere runc can fit in, you can swipe out and use Kata runtime. So let's imagine a scenario. You use Docker to create a Kata container, and at the same time, a lightweight VM has been set up. And you need to build communication between the host and the VM part. And the Kata agent is responsible for the VM part. Kata agent is a process running in the guest as a supervisor to manage containers and process running in the containers. It will communicate with other components while we SOC if your host supports. And the last part is Kata shim. If I understand correctly, I think Kata shim is just a bit little like the containerd shim. In runc world, containerd shim is the container reaper. It builds long-term communication between the container processes and the containerd. It will parse the I/O stream from the container processors into the containerd and deliver the signals from the containerd to the container process. But in Kata world, the container process is in the guest, so the containerd shim couldn't really touch them. So we need Kata shim to be the representative of the container process running in the guest, and to inherit the role of the containerd shim to be the container reaper. So enough talk about Kata containers design. Hardware requirements on ARC64. So the first point is that you only could run Kata containers on ARC64. Any 32-bit ARC version isn't under consideration. And you can use this simple command, Kata check, to test if system can run Kata containers. And the right side of my slide is the output of our partner machine. I couldn't tell you which machine because that's forbidden. So you could see from the first line, it says unable to know if the system is running inside a VM. So we have one limit for general 64-bit ARM machine. That's you could only run Kata containers on bare metal machine. Nested virtualization isn't fully supported. We have been working on that, but it's a long way. So here is one prefer. We strongly recommend you to update your host kernel version to the stable one. You pay attention here is the host kernel version to the stable one version 5.0. Why is that? Because it has the significant patch about increasing the IPA bits more than 40 bits. So why we need that CPU feature? Because in Kata world, we are continuously talking about large chunk device memory, like virtual NVDM, hot-ended PCD. So in previous kernel config 4.16, 4.19, the physical address for the virtual machine is limited to a static limit of 40 bits, which is definitely not enough for Kata world. So our kernel team has proposed these patches and got merged in version 4.20. In these patches, we also create a new I/O control request, KVM ARM get max VM physics shape to acquire your own system IPA limit. You should know that your IPA limit is dependent on your system. So different hosts has different IPA limits. Next, when you use KVM create VM to launch a new VM, you can pass the value into the type field, such like you pass the 42-bit IPA, and the VM you created will have the 42-bit IPA. So I will talk about NVIDIA on ARC64. That's one major work I have done in last year. So besides early days, besides AMD 64 or other ARM64 PowerPC will use what IOBLK to hold the guest root file system. And recently, we have found this fatal error. You couldn't launch more than 2 containers simultaneously because it could cause write lock error. So which means if every time you create a new Kata container, you need one new copy of the guest root file system in your memory. So that's memory disaster. You definitely don't want that. So we kind of forced to use NVIDIA on ARC64. So this is the basic design on NVIDIA DEX on Kata containers. The Kata containers use the QEMU NVIDIA features to provide a virtual device, a memory mapped virtual device that can map the guest root file system into the guest memory address space. And the most important here is the guest root file system could be shared within multiple containers. So no write lock error ever. And if you are enabling DEX, which means you could bypass the guest page cache and directly access the host memory pages, that's really reducing memory footprint. But unfortunately, this DEX feature isn't fully supported on ARM64, but we have working on that, and it will be very soon on public. So I will dig a little up on the status of NVIDIA, or generally speaking, persistent memories on ARC64. So, for real, before ARM version 8.2, until ARM version 8.2, we could fully support persistent memories. We could fully support non-volatile memory devices. Why is that? What's the new feature in ARM version 8.2? So to do the catch maintenance, we have two instructions: catch clean and catch invalidate instructions. Those instructions could be operated at different levels. Before 8.2, we have only two levels: POU, point of unification, and POC, point of coherency. So generally speaking, POU points to the L2 cache, and the POC points to the external memory system. So until ARM version 8.2, we introduced the new concept, POP, point of persistence, which is specifically designed for non-volatile memory devices. Along with this new concept, we also had added this new instruction, DCCVAP, to clean data cache by address to the point of persistence. If you want to detect your system, if it is capable of this CPU feature, you could use HWCAP or the CPU info file in the runtime. So this is last time I talked about we are forced to use NVIDIA on Kata containers, and until 8.2 we could fully support NVIDIA on ARC64. So does that mean any ARC lower than 8.2 couldn't use Kata containers? Yes, for the real hardware, NVIDIA couldn't work well on the ARM arc lower than 8.2, but the NVIDIA on the Kata containers is a virtual device created by QEMU, which lives in the host memory. So if your kernel find your system couldn't support DCCVAP, couldn't support persistent memory, it will use DCCVAC instead, which means the data cache line will be wrote all the way back to the host memory. That's where the virtual NVIDIA lives. So that's enough for the NVIDIA on the Kata containers. My another work is about memory held and on ARC64. Let me drink. It can be divided into two phases: physical memory held and phases, and the logical memory held and phases. The physical memory held and phases is about bridging communication between hardware and the kernel. There are two ways to complete this procedure: ACPI and probe interface. ACPI is the default option for Kata containers, but our QEMU doesn't support ACPI, so we switch to use probe interface. So ACPI will automatically notify the guest kernel about the newly hard-ended memory device. And the kernel, once the kernel recognizes the new memory devices, it will do some memory management, including makes sysfs files for new memories. And for the logical memory held-end phase, it is intended to change memory state into available for users. Kata containers, Kata agent has one Go routine, 24 hours listening to the memory hot and U event. Once they catch the memory hot and U event, they will unline them. But recently, communities have found this issue. If you hot block a big chunk memory device, such like more than 120 gigabytes, the Kata agent will be OOM killed. So we have been forced to set config memory hot block default online to turn them on guest kernel config to automatically unlock these newly ended memory devices. So about the implementation of memory held end on ARC64, there are two steps. The first step is about the preparation work. Is about the preparation work. We need to check if your guest kernel is capable of memory held end while probe interface. The Kata runtime will send the request to the Kata agent, and the Kata agent will to check the existence of the probe file, and if it will return the results back to the Kata runtime to store them for further use. The second step is about the true memory held end procedure. And you can see two colors in the flowchart, blue one and orange one. The blue one belongs to the ACPI, and the orange one belongs to the probe interface. So all methods start with the query the existing memory status of memory devices on your VM to acquire the next free slot for memory held end. When they get the free slot, it will try to device end the memory device. If success, ACPI will automatically notify the guest kernel about the newly ended memory devices. But the probe interface will don't have the automation scheme, so we need to manually notify the guest kernel. Here is how I implement the whole procedure. We need to query the memory devices, the status of memory devices in the VM again to acquire the starting address of the newly ended memory devices. Be careful here. If you hot plug an 30 gigabytes memory device, you need to divide them into small pieces based on the default size of the memory block. Different ARC have different size. For ARC64, we have 1 gigabyte for memory block. So that means we need to divide the 30 gigabyte memory device into 30 pieces and get the starting address of each pieces. And we need to send the addresses to the Kata agent, and the Kata agent will echo the address, each address, to the probe file. And that's the end of the physical memory held end phase. So I will do some sum up about the current status of memory held end on ARC64. It could be classified into 4 parts: the kernel part, the Kata runtime part, the Kata agent part, and the QEMU part. Our kernel team has proposed the memory hot block patch serials December last year, and it got merged in version 5.0. But this patches serials is based on ACPI driven, so we need to add extra probe interface on the Kata. About Kata part, my code, my work about last 2 slides about the whole implementation has been already merged, so you could see my code in the latest Kata version 1.6. The left part is the QEMU part. Thanks to the Eric Auger, he has proposed one large patch serials about including supporting NVIDIA, about reconstructing RAM map, about building up the memory hot block infrastructure for ARC64. This whole patch series has been under review. Some already got merged, some has been under review, and I'm thinking it will be all merged in QEMU version 4.0, so not a long way. And that's my parts. I will hand off to my coworker, Justin.
Hi everyone, my name is Justin, and I work for ARM China for nearly half a year, and I'm mainly focusing on the Kata Container and Unicraft. Thanks for Penny's work. Then I will elaborate more about what we have done in Kata on ARM64. Here's the agenda. Firstly, I will introduce something about the CPU hot plug in ARM64 QEMU. Secondly, is about VM templating. The third one is SIIOV virtual function hot plug. And last, I will give you a to-do list in the future. This is the architecture of, to speed up the VM creation, Kata will start a VM with limited resources, such as one vCPU, 128 megabytes memory. The memory hot plug has been covered by previous slides, Penny's slides. And then we will come to the CPU hot plug. The vCPUs will be dynamically assigned when Kata Container wants to update resources. In my opinion, the best solution might be the ACPI-based CPU hot plug, but there are some limitations on ARM64 which cannot be overcome so far. The first one is the ACPI-based CPU hot plug has not been supported in QEMU guests so far, and even no clear plans for future. The second one is ARM GIG architecture. GIG means generic interrupt controller. GIG architecture cannot handle the hot adding vCPUs after booting. The data structures for the vGig needs to be physically and contiguously allocated, which means we need to define the maximum number of vCPUs in advance. Here are some comments from Mark and Christopher. The conclusion of their comments is that the vCPU number should be available before the vGig is initialized. So the best way might be closed. So here is my proposal. Frankly speaking, it might not be the perfect one, but seems to be the only feasible one on ARM64 so far. Firstly, when the change in the QEMU starts a VM with parameter -SMP4-append max CPUs equals to 1, it can create 4 vCPUs in device tree. This works around the vCPU reinitialization limitation at a vGig side. Then the guest kernel will be started with 4 CPUs, but only 1 is online. The rest of 3 are set to offline. Kata uses a QMP command, query hot pluggable CPUs to get the pluggable CPUs info in the guest. When the QMP command device add or delete is triggered, the QMU will be notified, but the CPU in the guest will not be physically added or deleted. Then Kata runtime uses gRPC protocol request to communicate with Kata agent side. And the Kata agent will set the wanted CPU to be online or offline. At last, in the hot plug removing case, QMU will send a special device deleted event to Kata. Currently, all the required vCPU resources have been reserved after the guest starts, but the user in container can only use the online ones. Here is a summary for the pros and cons. The pros are such as the hypervisor doesn't need to support the ACPI-based or other hardware CPU hot plug. This is really helpful to ARM64 or even Firecracker, which doesn't support the CPU hot plug. And the code is easier to implement. And, but still, there are some cons here. The first one is it might have impact on the container density on ARM64. And still some concerns from the community, such as this is just a orchestration workaround instead of a hypervisor solution. They might prefer a hypervisor solution. And they also concerned about the security issue because they don't want to let the container user to control the CPU resource. The second item is about VM templating. VM templating is a Kata container feature that enables new VM creation using a cloning technique. When enabled, new VMs are created by cloning from a pre-created template VM. And they will share the same initial RAM FS, the same kernel, and even the agent memory in read-only mode. It is just like process forking by the kernel, I think. This feature is firstly introduced by Lai Jiangshan, and then Pen Tao pushed it into Kata's QMU. Finally, upstream merged URI's commit maybe in February this year, 2019. But still more work is needed to improve this feature on ARM64. After URI's commit, it adds ignore shared capability to bypass the shared RAM block. For example, memory backend file with the flag share equals to on. It does good to live migration, and also it is the base of the VM templating. The root cause is that it is expected that QMU doesn't or shouldn't write anything to the guest RAM until VM starts, but it really does in ARM64 QMU. For example, in the virtual machine, the ROM block DTB, which contains the device tree information, will be filled into RAM during room reset. So in incoming case, The room filling seems to be not required since all the data has been stored in memory backend file already. Catherine submitted a proposal to fix this issue, which is still under upstream review. The SRIOV enables splitting a physical device into virtual functions. Virtual functions enable the direct pass-through to virtual machines or containers. For Kata containers, we enable a container network model plugin. That is, we can pass through the virtual functions of a network interface card into container. On ARM64, it bases on Eric Auger's work in year 2016. It's about the KVM PCIe or MSI pass-through in both QEMU and kernel side. This is an example command to create a container with SRIOV virtual function pass-through via VFIO infrastructure. If we don't pass a MAC address to virtual function link, the virtual function driver in the guest kernel, for example, Manilogs file, might generate a random MAC address, which is definitely different from the host one. So the failure here, the Kata runtime and agent will use the MAC address as the top priority to identify whether the link is the same or not. Then the virtual function device cannot be passed through into the QEMU guest. Here is the proposal, which is still under development. That is, use the PCI BDF address to search the link instead. That is not the MAC address. Finally, here is the to-do list on ARM64 in the future. For example, the virtual I/O FS items, which is might be the hot topic in the community currently. And second, such as the NVDIMM DEX support. Actually, the kernel side, the patch series is under internal review from Anshiman. And the QEMU side, the patch set has been sent out, and I think more comments are needed here. We also need to support some light-weighted VMM, such as Nemio and Firecracker. We also need to run the Kubernetes integration test. And another useful tool to measure the booting time or the memory footprint metrics, which is not supported on ARM64. So that's all. Is there any question to me or to Penny? Oh, okay.
Thank you. Can I?
Penny?
Thank you. Can I ask how many requests have you seen for SRIOV support for containers?
Yes. Okay.
Have you seen a lot of requests for SRIOV? Many requests? Have you seen many requests for it?
How many email requests for SRIOV?
What do you mean, the request from the customer or?
A large number, a small number of requests?
Maybe use the SIOV virtual function hot plug to create the network. It is to save the memory footprint. But from custom side, there's no customer request to ARM64 so far, I think.
Okay.
Sorry.
I think in general, people who are more in PNS, there are people, as they look at different PNS local apps, these people do, but the standard off-the-shelf services, it's not very
We use the mic for recording, please.
I was just going to say that for NFV or like VNF chaining and stuff like that, people do it, but to traditional microservices, it wouldn't be a very typical request.
Thank you. I was wondering in that vein if it's something that maybe containers could grow into offering that wasn't traditionally thought for them to be able to offer things like SRIOV performance. So thank you.
Thank you. Oh, thank you all.